Okay, for this video, we're going to talk about how to find limits analytically. And the first thing that we do with limits when we're not having a graph here and we really don't want to generate a graph is we can do a direct substitution. Sometimes this works, sometimes it doesn't give us an exact answer and we have to try something else. So for part A, we are going to do always a direct substitution, and that's how we'll start every problem. So here we want to know what this limit is. Now this is a nice, neat polynomial. Here it's a parabola when graphed, and so we should get a nice, neat answer when we plug in. So we're going to have 3 times 2 squared minus 5 times 2 plus 4. And when we work all that out, that should generate for us, looks like we're going to get 6. So notice for part A, pretty straightforward here. We're just going to plug in and work out. And the same is true for part B. We're going to plug in and see what we get. So we're going to have a fraction, and we have 2 to the 3rd power plus 1 all over 2 plus 1. And so when we work that out, it looks like we're going to get 9 over 3, which gives us 3. So that limit is 3. All right, part C, the limit as x approaches e. So again, we're going to do our substitution. That's going to give us the natural log of e all over 3e. Now, some of us are probably not going to remember this, but the natural log of e every single time is 1. And so that's going to be 1 over 3 times e, which is a nice, neat number, and so you're finished. Okay, same for d. I'm going to substitute in my 4. So that's going to give me the cube root of 4 plus 4, which is 16. So I don't need that ginormous root there, do I? So, or 4 plus 4 is 8, not 16. Sorry, crackhead moment. And the cube root of 8 is 2. So that's going to give us a nice, neat answer. Oh no, we have a trick here. So let's substitute this in. So I'm going to have the sine of 2 times pi over 6. And so we're going to cancel that 2 with that 6. So that's really going to give us sine of pi over 3. And sine of pi over 3 is the same thing as asking sine of 60 degrees. And that's going to give us square root of 3 over 2. All right, and then our logarithm, we're going to substitute in our 5. So I'm going to have log base 3 of 5 plus 4, which is 9. And now a little bit of review here. This is saying 3 to what power gives me 9, and that what power is 2. So my final answer there is 2. Now sometimes when we plug in, we're going to find some points that might generate some discontinuities, or a non-removable discontinuity, or something called an infinite discontinuity. So we're going to examine what all of that means. Okay, so let's look at this problem here. And we're going to go ahead just like we were before, and we're going to substitute in 2 into our limit to see what we get. So in the numerator, we're going to have 2 squared plus 2 minus 6 over, again, 2 squared minus 6 times 2. So that's going to give us 12 plus 8. And notice what happens here. We end up with 0 over 0. And when we have that, that is going to be an indeterminate form. And anytime that we have our indeterminate forms, that means we have to do something else. This is never ever 1. It's never ever 0. This, again, it's an indeterminate form. So do keep that in mind when we go through these. Not everything that we run into is indeterminate form, but if we have something of this nature, then that means we need to do something else to find our answer. And so when we do run into that, when this happens, you need to go through maybe and factor. And so we're going to factor the top and bottom and see what happens with this. And of course, we have our graph down here below. But Let's start out with the factoring. And so I'm going to move down to the bottom part problem here. And we know if direct substitution we get 0 over 0, that's not going to work for us. So what I need to do is factor the top and bottom and do some kind of canceling. So over here to the side, I'm going to factor this. And I'm going to get x, let's see, it looks like we're going to have a plus 3 times an x minus 2 over an x, looks like minus 4 minus 2. And so we see very quickly that those minus 2 should cancel. So now I'm going to come back and I'm going to rewrite this limit to be the limit as x approaches 2 of this reduced rational x plus 3 over x minus 4. And now when I substitute in our 2, we're going to get 5 over negative 2. So once we do that, then we're going to find that this does have a limit. And over here to the side, the graph is demonstrating what's going on with this. What it's doing is showing us that we do have this point of discontinuity at 2 and negative 5/2. So right there, that's what we've shown in this very first example. So let's look at what happens now as our value, as our x value, is approaching 4. Well, we see that we have just our one-sided, and we also see that if we plug in straight into our function, which let's go ahead and use the reduced form. So I'm going to bring down this limit as x approaches 4 from the right of x plus 3 over x minus 4. Now, if I substitute in a 4 right here, I'm going to get 7 over 0, which tells me that if I have a 0 in the bottom, I have a vertical asymptote. My answer, every time I see this, will either be a positive infinity or negative infinity. The only way I'm going to know which one it is to plug in a value just to the right of 4. And I say the right because it has the little plus sign. So a number just to the right of 4, well, that would be 4.1. Or we could do 4.11. We could do 4.001. It does not matter, just as long as it is a number to the right of 4. Now, when we do that substitution, what we're looking for is a positive or a negative value. That's going to tell me which infinity I need to pick. So let's plug in, let's just say 4.001. Let's just get really close. And where we're plugging it in is this value right over here. So if I do that, notice I'm going to have on top, let's see, if I plug in 4.001 plus 3 over 4.001 minus 4, really all I care about is this positive or negative. Well, it's going to be a positive, so that tells me that from the right, as I'm approaching 4 from the right, I have positive infinity. And I know it's positive because after I substituted in all this gobbledygook, all of that was a positive value. And if we look over here to our graph that we're given, we see that that does indeed tell us what we needed to know, which is that graph is approaching positive infinity. So technically, we can figure out some of these limits without ever having the graph. Okay, so hopefully when we apply that same idea as we're approaching from the left, we should get negative infinity. Now, it doesn't always alternate. Sometimes it's both positive, sometimes it's both negative. And so we're still going to look at the limit as x approaches 4 from the left. And again, we're going to use our reduced form, the x plus 3 over x minus 4. And let's substitute something to the left of 4. So we could try maybe 3.999. Let's try that. So I'm going to substitute in 3.999 plus 3 over 3.999 minus 4. And again, all I care about is whether or not this is positive or negative. On top is positive, but notice on negative in the bottom, we're going to get a negative. So that tells me this is tending toward negative infinity. And if we look at our graph, we see that that graph does verify what we found. Okay, so after we've gone through all that, we see that there are some discontinuities we can remove and some that we can't. The non-removable, the one I could not get rid of, that's going to be what we call a vertical asymptote. So let's get that written in. We're going to have a vertical asymptote, and that's because I cannot remove it from the function. And so whenever we have that vertical asymptote, this is going to occur at x equals 4. This is what we just looked at. We say that the limit does not exist because the y values do not approach, or y values do not approach one value. And it's because that value that it's approaching, that is going toward infinity, which infinity is not stopping. All right, so when x equals 2, which is going to be where we were able to cancel out, and that gave us a hole in the graph, then that canceling part, that 2, that is called a point of discontinuity. And we did talk about that in pre-cal, but we are reviewing it for pre-cal and making sure our Algebra 2 kids know it. Okay, here at the last part, it's asking you what observations can you make about analyzing functions to find limits. And it says, do you see a type of process developing? Hopefully, with our limits, we will see that with those, our first line of defense, the first way we attack limits is going to be to plug in. Each and every time you plug in. And then from plugging in, we run into a few things. One thing, if we plug in and we get a nice, neat number, yay, you are done. That is your answer. If you plug in and you get 0 over 0, well, that means that you probably need to factor and cancel and then replug in because something's going on there, and it's probably a hole in the graph. It's probably a removable point of discontinuity. And then the other option you might run into with straight plugging in is you might get a number over 0. And when that happens, then we probably have either does not exist, or if it's one-sided, we could have positive infinity or negative infinity. And then that just means we have to plug in a number and just pick and see, well, which one is it? Right, so this is kind of the idea of what we have for limits. Now let's look at some limits that might be a little more picky. Right, so let's go back to our example and make sure we see how this is all fitting together. So again, our first line of defense would be to straight plug in, but if we plug in a 4, we're going to end up with something weird. If we plug in 4, let's see, it seems like we're going to get, on top we have 16, don't we? And then plus 4 minus 6. So that's going to be, let's see, 14. But in the bottom, we're going to have 4 squared, 16, minus 24, plus 8. So we're going to get 14 over 0, which means we got a problem. So we need to plug in. But I also noticed that this is something that we could factor, and we can simplify this down. And I think earlier we did factor that down, and we had something nice and neat, like it was x plus 3 over x plus 4, or x minus 4, excuse me. So, but we would still, after we plug in, we're going to get, if we plug in a 4 here, we're going to get 7 over 0. So no matter which one you use, you are still getting a number over 0, which means that we have a vertical asymptote at x equals 4. It's a non-removable discontinuity. So, again, that's why we had to analyze these numbers to the right of 4. And you could pick something nice and neat like 4.1 for x. So we could let x be that. And again, plug in, and we have 4.1 plus 3 over 4.1 minus 4. And notice that gives me a positive value. So that tells me that my answer here is positive infinity. And again, we did the same thing over from the left side. And from that left side, we said we could pick 3.9 for x. And I'm going to plug it into the simplified version to make it a little bit easier. So I'm going to say plus 3 over 3.9 minus 4. And again, notice that this is going to give me a negative value. So that's why we said negative infinity. So again, we need to be careful there. And down here at the bottom when it's asking us, well, what was that limit value? I had rather y'all say, well, from this, since it's a one-sided, it's positive infinity, and on the left side it was negative infinity. And here's how we saw that that would be the correct answer. Okay, now here's another example of some weird stuff. The graph of g of x is over to the side, and notice that is wanting us to find the limit as x approaches negative 1. But if we plug in negative 1, let's go ahead and try our very first line of defense. I don't think it's going to work, but let's try it. That's going to be the square root of negative 1 plus 2. So square root of 1 minus 1 over negative 1 plus 1. So that tells me I have 0 over 0. So I need to factor this. However, looking at this, this probably will not factor. So we're going to have to do some algebra magic here. So let's see what some algebra magic can do. We are going to do some sort of rationalizing, but we're going to rationalize using the numerator. So let's see what that looks like. So I'm going to have the square root of x plus 2 minus 1 over, and I'm just recopying the problem. Now when I rationalize, y'all are used to using the denominator, but I'm going to use the numerator just because we're weird. And I'm going to change the sign in between to make it plus 1, then plus 1. Now, I'm going to save us some time here and tell you what happens. You would normally have to FOIL this gobbledygook out. But in that process, you should get stuff to cancel, and it will cancel every time. So to save us some time here, all you have to do in this situation, let's multiply the square root of x plus 2 times the square root of x plus 2, and those radicals cancel each other out, and you're just left with x plus 2. I'm not going to worry about the middle term because that thing is going to cancel every single time. So then I'm going to worry about just these outer terms, which is going to give me negative 1. Now what about the denominator? Well, this is a bunch of ugly stuff, so I'm just going to bring over my x plus 1. I'm not going to multiply it out. Math in calculus, you do as little number crunching and algebra as possible. So I'm just going to bring that over. I know it's lazy, but that's what I'm going to do. And so in our continuing to simplify some of this, notice this numerator here. That's really becoming x plus 1 over the denominator is x plus 1 times the square root of x plus 2 plus 1. And oh my gosh, look, lo and behold, those are going to cancel. How wonderful is that? And so now let's go back and look at our limit. As x approaches negative 1, and I'm going to have 1 over the square root of x plus 2 plus 1. Now let's reevaluate that limit, and it looks like it's going to work out nice and neat. When we plug in negative 1, so I'm going to have 1 over, that's going to be the square root of negative 1 plus 2, so square root of 1 plus 1, and lo and behold, it works out to be nice and neat. So look at the strategy that we did here. We just ended up doing some kind of rationalizing that we just rationalized with the numerator instead of the denominator. And then knowing that that middle term will cancel every time, we are just going to shortcut this down and multiply my first terms and my last terms. And when that happens, you should have some kind of awesomeness to happen. Now, what is going on with this related to the graph? Because we do need to go back and relate to the graph if we can. And notice that at this point here at -1, and at 1/2, that's 1/2 there, that's where we have a hole in the graph, which that hole is corresponding to the 0/0. That's what it was telling me algebraically when I substituted in and got 0/0. So that's why we had to do the algebra magic. And through that process, this limit ended up being the y coordinate of the hole. And let's go ahead and write ourselves a reminder of that. That is the y coordinate of the hole, or y coordinate of the discontinuity. Why don't we call it that? And I'm going to run out of room. Alrighty, let's try another one. Alright, again, always a good idea to try to substitute in because sometimes they try to trick you. Well, the numerator, we're going to get 5 minus 5 over, over 3 minus the square root of 9. So we are indeed going to get 0/0. Now be careful, kind of a side note here, if you get 0 over any other number, then your answer is 0. So you could get an answer of 0 there, so watch out for those traps. All right, now we're going to come back and do our little algebra magic again, but this time notice where the radical's at. It's in the denominator. So we're going to rationalize that. So we have x minus 5 over 3 minus the square root of stuff. And we are going to rationalize that with 3 plus square root of stuff over square root, my gracious, 3 plus square root of stuff. All right, so let's see what that gives us. And again, I'm just going to multiply this across. I am not going to fool out anything. Don't be a crackhead. Don't fool out stuff. Just leave it like it is. All right, and then in the bottom, again, this stuff right here, 3 times 3, just multiply the first terms, that's going to give us 9, and then just multiply the last one. So a negative times a positive is a negative, and the radicals will cancel each other out, and I have x plus 4 left. All right, so let's go ahead and keep our simplifying going. So I'm going to have x plus 5 in the top. Or I'm sorry, I don't know where the plus came from. X minus 5, times 3 plus square root of stuff, x plus 4. And then that is all over, let's see, this is going to be 9 minus x minus 4, so plus 5. And I see something that can cancel. I see some opposites. These are opposites, so that means they will cancel. But I have a -1 left. Now I'm going to let that -1 sit out there. And now that I've done that algebra magic, now I'm going to reevaluate my limit and see what I come up with. And so again, I've got the limit as x approaches 5. So we're going to go back and do that one. Limit as x approaches 5. And I'm just going to copy this down. We've got -1 from canceling times 3 plus square root of x plus 4. And now substituting in that 5, I have -1 times 3 plus, and the square root of 5 plus 4, that's 9, square root of 9. So then that's going to be what, 3? So my final answer is -6. All right, so again, we started out with the 0/0, and we saw we could work our way around and actually find what that answer is. Okay, now let's put all the different types of limits together. So here, starting out, we have our -2. And notice this isn't a square root. There's not any fractions. So this should be, since it's a polynomial, a nice, neat limit. So let's go ahead and see if we can't get it to work out that way. So let's substitute in -2. And so -2 to the third power, that's going to be -8 plus 3 times -2 squared. Let's see, -4 times -2, that's +8, and then plus 5. So that worked out to be 17. So that's nice and neat. Same is true with b. It's a nice, neat polynomial situation here. So now do keep in mind when you square that fraction, and you could see that. This is 2 times, now 3/2 squared, you just square 3, square 2, and then times, and then here 2 times 3 over 2. Those 2's are going to cancel, so you just have 3 plus 3. And once you simplify all that, you should have 27 is what it looks like. All right, so again, traveling on, again, C should be something nice and neat. I don't see any fractions. Now part D, I see some fractions. But here part C, again, substitute in. So that's going to give me 15 plus 1 or 16 raised to the 2/3. And this is a good review. Remember the roots grow on bottom. That's the root. 2 is your exponent. So here we have the third root of 16. And then we need that all squared. And a lot of times on the exam, you will see it either just left 16 to the 2/3 or written this way. And that's simplified enough. Now, if you really feel froggy about it, it does end up being 4 on the cube root of 4, but that's not necessary. You're more than welcome to leave it one of the first two ways. All right, now let's see. I get super suspicious when I see something like part D. And honestly, I go ahead and I factor it. So I'm going to come down here, and this 2x squared plus 7x minus 4. I'm going to factor that, and I always factor it bottoms up or slide and divide, either way. So I have x squared plus 7x minus 8. And so I see that that's going to factor into positive 8 and negative 1. And then I come back and divide by 2 because that's what I multiplied over by. And so let's see, that's going to give me factored form x plus 4. And then over here, remember to move that 2 up after you try to reduce, and you get 2x minus 1. All right, so let's see what we ended up with here, because we can factor the other one pretty quickly. So I have the limit as x approaches negative 4. In the top, we got to be x plus 4 times 2x minus 1. All over, and that bottom's going to factor to be x minus 5 times x plus 4. All right, now let's look at what we're approaching. We're approaching with negative 4. So if I plug in negative 4, I'm going to get a 0 on top and bottom, but we see that those will cancel. So now let's talk about just that good old limit as x approaches negative 4 of 2x minus 1 over x minus 5. Now we can substitute in, and when we do that, let's see, we're going to get negative 8 minus 1, so negative 9 on top. And then in the denominator, once we substitute in, we get negative 9. So that limit is positive 1. Okay, with these problems, it looks like we might have to do some rationalizing. We can do some substitution first just to see. If we substitute in 3, it looks like we're going to get 2 minus 2 in the numerator and 3 minus 3 in the denominator. So we get 0 over 0 again, which is not 1. It's an indeterminate form. So down here, we're going to simplify this a bit. We're going to rationalize the numerator. So I'm just going to bring down the problem. And then I'm going to multiply the top and bottom by the complex conjugate. So I'm going to have x plus 1. Just change the sign out here. And the same for the denominator. You want to make sure the numerator and denominator are the same. And when I multiply these, again, I'm just multiplying the radicals together, which should cancel out and just leave x plus 1. And then negative 2 and positive 2, which is going to give me a negative 4. And then in the denominator, I am going to multiply this and this part, but I'm not actually going to multiply it out. I'm just bringing it over. And let's see. Now we should be able to do some more simplifying in the numerator. It looks like I'm going to end up with an x minus 3, which is great because I have an x minus 3 in the denominator. And hopefully y'all are seeing that there's a pattern with this, that you should be getting things to cancel when you have to rationalize. And so now let's go back and reevaluate our limit. So now we're going to talk about the limit again as x approaches 3 of 1 over the square root of x plus 1 plus 2. And once we now re-sub in, it looks like we're going to get 1 over 2 plus 2, or 1/4. Okay, so let's go ahead and do the same thing over here with part F. And again, it does look like that when we sub in, we're going to get 0 over 0. And you can look at it and verify that. And so let's go over and pull this down and do some rationalizing again. And I'm going to multiply top and bottom by the square root of x plus 4 plus 2 over the same amount, x plus 4 plus 2. And so again, we are just going to multiply the radicals together. So I have x plus 4, and then just these together, minus 4. And then in the denominator, x times square root of x plus 4, then plus 2. And then we see these 4's will cancel each other out, that you have an x left, and then that x will cancel down here. So it looks like we have 1 over the square root of x plus 4 plus 2. Now we're ready to reevaluate our limit as x approaches 0. And we're going to have of 1 over our reduced form, square root of x plus 4 plus 2. And when we make that substitution, it looks like we're going to end up with 1/4. All right, so for part G, again, we need to plug in. Always start off by plugging in. Now, this one looks like we're not going to get a whole lot. This looks like fraction on crack. Let's see, over 0. Now, a lot of people want to try to do something with this. You really can't do anything with it. This just tells me, really, with that 0 being generated in the big denominator of it all, that's telling me we probably have a vertical asymptote somewhere. And when we have a vertical asymptote here, then that tells me I need to pick some values. Now, we could do a bunch of algebra crap, but it really gets messy here. And it would be a lot easier to pick values. And you're probably going to end up with either positive infinity or negative infinity for an answer. So let's go over and let's look at just our one-sided. So I'm going to look at the limit as x approaches 0 from the left of all this stuff. So 1 over x plus 3, and that's all over x. So what I'm going to do is let x be something just a little bit to the left of 0, maybe negative 0.01. And let's plug in and see what we end up with. So if I substitute in, I'm going to have 1 over negative 0.01 plus 1 over negative 0.01 plus 3. And then that is all over negative 0.01. So let's see if we get a positive or a negative in that. Okay, so let's see. this first part here, 1 over negative 0.01. Remember that means that we're moving our decimal, and so we would have to move it to the right 2 places and attach our negative. So that's really going to be negative 100 plus, now over here that's really just going to be 1 over 2.99, isn't it? Yep. Okay, so that's all over negative 0.01. So all of that, when it's all said and done, this is going to still be negative in the numerator. In the denominator, it's negative, so that's going to be a positive. So from this side, that's going to tend toward positive infinity. Okay, now let's look at it approaching from the other side. So same idea here. We're going to do the limit as x approaches 0 from the right of our same function, just to see what in the world is this thing approaching. All over x. So why don't we let x be the positive version of what I had, 0.01. And if we do that, that will hopefully tend to make things a little bit easier to work with. So that's going to be 1 over 0.01 plus 1 over 3, if I go ahead and add those, 0.01, all over 0.01. So notice again, all of that gives me a positive over a positive, which is going to give me positive infinity. So notice what's happening here. Both sides are tending toward a positive infinity. So based on our limit from the left is equaling the limit from the right. So this entire answer is going to be positive infinity. All right, not all problems are that endowed though. It just happens to be this one. All right, H, notice it's a good indicator the way the setup of the problem is that we need to do some kind of factoring and canceling. All right, so let's go ahead and factor this, and I think we're used to that slide and divide or bottoms up. So I'm going to rewrite that to be x squared minus 7x plus 6. Now when I factor that, it's going to be negative 6 and negative 1. Now don't forget to come back and divide by 3, and whatever doesn't reduce, you have to move it back up. So that's going to give me x minus 2, and that 1/3 does not reduce, so I'm going to get 3x minus 1. All right, so now we're ready to do some reducing. Here we've got the limit as x approaches 2, but now this is one-sided. I'm coming in from the positive. And let's see, what did we get in the numerator? We had x minus 2 times 3x minus 1. And that is all over, and the difference of 2 squares, so we have x minus 2 times x plus 2. Notice these 2's will cancel, yay. And so let's see what our limit is. So let's go ahead and plug in 2. Now it's from the right side, but when I plug in a 2, I'm not getting a 0 anywhere, so it's okay just to go ahead and substitute it in. You're only picking values like we did in the other problems is because we were getting a 0 in the bottom. Here we're not going to. If we do our substitution in the top, we're going to get 3 times 2 minus 1, so that's going to be 5. And in the bottom, I get 4. So now we're finished. Okay, moving on to J. Go ahead and plug in your 5, even though it's one-sided. So let's go ahead and see. My pen is going crazy, folks. Hang on. I think my pen is starting to protest. It's so done with math. All right, so if I go ahead and sub in our 5, we're going to get a problem here. So let's see. That's going to be 23 in the numerator over 0. All right, number over 0 right there. So that tells me I have a vertical asymptote. That means that I need to plug in some values. We need to plug in some values. And that also is telling me that I either have a positive infinity answer or a negative infinity. And it all, again, is a vertical asymptote. All right, so let's see. Over here, a little bit to the right of 5. So why don't we let x equal maybe 5.01. That might help us see. And we're again looking to see, do I get a positive or a negative? So we're going to have 4 times 5.01 plus 3 over 5.01 minus 5. And I don't care to work it out. There's really no need. Look at what you get for your signs. And the numerator is positive. 5.01 is bigger than 5, so it's positive. So notice that's both positive. So this answer would be positive infinity. All right, and it looks like K is kind of the same idea, but again, we're approaching from the left side. So let's plug in a number from the left. So let's let X be 4.9. And when I plug in 4.9 into the top, it's going to be times 4 plus 3, which is positive. And then I have 4.9 minus 5, which is going to give me a positive over a negative, which is negative. So that means this side is tending toward negative infinity. Okay, now we're going to talk about finding limits analytically of piecewise functions. And this is where knowing that formal definition of finding a limit is going to come in handy, because we need to talk about here, when you have that, you're going to talk about the limit as x approaches 1 from the left of whatever your given function is. And then you'll talk about the limit as x approaches 1 from the other side of the given function. And then you're going to compare the two and see if you get the same answer. So the biggest part of this is realizing if you're coming in, if x is approaching 1 from the left side, then this is really talking about when x is less than or equal to 1, or just x is less than 1. So that tells me that I need this portion. Those two are matching. So this is the function, that's the part of g of x that I need to plug into. And what I plug into is just 1. So I'm going to get 1 plus 1, which is going to give me 2. So, and I'm going to change colors for this other one. It's going to be the same idea. Notice you are approaching from the right. So that tells me that I'm looking for when x is greater than or equal to 1, or just x is greater than 1. Which is going to be the top part of this. That's why you've got two different parts that you have to look at. And so that tells me I need to plug into the x cubed plus 1. So x cubed plus 1, if I plug in 1, that's going to be 1 cubed plus 1, which is 2. So the way you complete this one, you see that the limit from the left is 2, the limit from the right is 2. So then you can go ahead and make that formal statement that the limit as x approaches 2 of g of x is going to be 2. Not approaches 2, approaches 1. Sorry, my crack's wearing off. All right, so same idea over here in part B, using that same setup. So the first thing I need to do is look at my limit as x approaches 2 from the left of h at x. And that just means which side of the inequality do I need to be. I need to be on the left side, so that's going to be this portion. So I plug in 2 here, and I get 2 squared. So I have 4 minus 2 times 4 plus 7. So it looks like I'm going to get 3. So then we also need to check from the other side. So we have the limit as x approaches 2 from the right side of the function. So that means I need a greater than situation if I'm on the right side of 2. So here I plug in and I get negative 4, and then plus 8 minus 1, and there again we get 3. So notice these things are matching. So then I can come back and say, well, the limit as x approaches 2 of my function is actually 3. Okay, continuing this on, again we're looking at our limit as x approaches negative 3. So again, our setup, we have the limit as x approaches negative 3 from the left of our function f at x. And notice for this one from the left, we have the setup, which means we have something here we need to factor. And so I'm going to go over here to the side, because if I plug in -3 here, I'm going to get 0 over 0. So I need to factor this. Well, x squared minus 9 is going to be x minus 3 times x plus 3. And that is all over x plus 3. So those are going to cancel. So really that whole thing simplified down to be x minus 3. So down here, when I substitute in now my -3, I'm going to have -3 minus 3. So from that side, I'm going to get -6. Then I need to go change sides, and I need to look at my limit as x approaches -3 from the right of the function. And let's plug in our -3, so I'm going to have positive 9. And once I square it, and then I'm going to have -30 plus 15. And it looks like we're going to get -15 and 9, so I'm going to get -6 again. And I wrote 9. Goodness, -6. So notice these two do equal each other, so we can come back with our formal limit as x approaches -3 of f of x equals -6. Okay, again, now look at part D. D is a little bit different. Notice the difference is we don't have inequalities over here. So what that means is we're still going to look from the left and right, but notice that the only time we're ever going to swap would be if we're looking at when x is actually 1. So here, when we look at our limit, as x approaches 1 from the left of g of x, we're still going to plug in here. We're still plugging in there. And so whenever I plug in 1 there, I'm going to get a 5. And then again, over on the other side, the limit as x approaches 1 from the right side of g of x. Again, I'm still plugging into the same place. And so I see that my limit as x approaches 1 of g of x is indeed 5. Now that one looks weird. If we draw a picture of this, let's go over to the side and just draw. What in the world does this look like? Well, we know that x squared plus 4, that's a parabola that's been moved up 4. So let's go over, or we don't go over any, we go at 1, 2, 3, and 4. And so I do have the parabola, but I should have an open circle. I can't use one, but I need to pinpoint, well, where is that hole at? So if I plug in, I get the whole 1, let's see, 1 and then 1 plus 4, so 1, 5. So I go over 1, and at 5, which is one more here, I have an open circle. But on each side of that, I've got my parabola. And I've got my parabola here. And then it's telling me at that point 1, I have a y value of 2. So here's what the graph actually looks like. So now we're not continuous at 1, but our limit certainly exists, and it exists at that whole value, which is at 5. And finally, we're at our last two examples. And again, it's piecewise, so we do need to look at both sides. And so for the first one, I have the limit as x approaches 0 from the left of our function f of x. And so from the left, that means I want all the values less than. And so notice it's e to the 2x. Now don't freak out when you see that. Let's plug in and just see. E is a constant value, just like pi is. And it's raised to the 2 times x, or 2 times 0, which that's going to give me e to the 0. And again, we're going to use that exponent rule that tells me that that is 1. And notice, even though it had an e there, it was kind of intimidating, but it wasn't too bad. Now let's look at from the other direction. We have the limit as x approaches 0 from the right of our function. And so that means I need this portion down here. And so when I plug in, I have 0 times e to the 0 power. Well, that's going to be 0 times 1, which is 0. Uh-oh. We don't have these two matching. So we're going to say that the limit as x approaches 0 of our given function, it does not exist. Does not exist. Why doesn't it exist? Well, the limit from the left did not equal the limit from the right. So they're approaching two different y values. Okay, our last example, same notion again. We're going to have the limit as x approaches 2 from the left of h at x. And so I need less than 2, so let's substitute in. So I'm going to have 1/2 times 2 squared minus 1. So that's going to give me 1. And now let's look at the limit as x approaches 2 from the right of h at x. All right, so from the right, we have this up here. So that's going to give me 3 minus 2, which is 1. And yay, these do match. So I have the limit as x approaches just good old 2 of our function h at x. I wrote straight to right enough. H at x, and it does indeed equal 1.